traveler. Tonight we journey to the heat death of the universe. You have nothing to do but rest. Let your breathing slow, let your thoughts grow quiet, and let the cosmos carry you gently to sleep. There is no hurry tonight, no deadline, no alarm waiting at the other end of this journey. You are exactly where you are meant to be, resting, listening, drifting. If you are lying down, let the weight of your body press gently into whatever is beneath you. Let the mattress, or the pillow, or the floor hold all of you, every kilogram, every worry, every thought you carried through the day. You do not need to carry anything now. You can set it all down, the way you would set a heavy bag beside a door and walk away from it, knowing it will still be there tomorrow if you need it, but tonight, you do not need it. Let your jaw unclench. Let the small muscles around your eyes soften. Let the space between your eyebrows become smooth and wide, as though someone very gentle has pressed a warm thumb there, and all the tension has melted away. Your shoulders can lower, not all at once, just a little, a few millimeters at a time, as if the day's weight is slowly sliding off the edges of you. Your hands can open, your fingers can uncurl, your wrists can go soft. And your breathing, you do not need to control it, just notice it, in and out, in and out. Each breath a little slower than the last, each exhale a little longer, a little quieter, like a tide pulling gently back from shore. The room is still around you, the air is calm, the world outside can do whatever it does, but here, in this small space, there is nothing but quiet. And into that quiet, we are going to tell a story, the longest story ever told, a story that stretches from now, from this very moment, all the way to the end of time itself. It is not a frightening story. It is not urgent or dramatic. It is the most patient story the universe has to offer, a story about cooling, about dimming, about the slow, inevitable, beautiful settling of all things towards stillness. Scientists call it the heat death of the universe, but you can think of it more simply than that. It is the story of how the cosmos, having created everything it will ever create, having burned every fuel and lit every star, will eventually find rest. The same kind of rest you are finding now. So let us begin, not at the end, but here, in the present, in the age you were born into, the age of light. Right now, at this very moment, you live inside the most luminous chapter of the universe's existence. Scientists call it the Stelliferous Era, the age of stars. Everywhere you look in the night sky, if you are far enough from city lights, you see them, thousands of tiny points of light scattered across the dark. Each one is a sun, many of them far larger and brighter than our own, and each one is burning, converting hydrogen into helium deep in its core, radiating heat and light outward into the void. Our galaxy alone, the Milky Way, contains somewhere between 200 billion and 400 billion stars. That number is so large that if you tried to count them, one per second, without sleeping, without stopping, it would take you more than 6,000 years to finish. And the Milky Way is just one galaxy among trillions. The observable universe contains roughly 2 trillion galaxies, each one a vast island of stars, spinning slowly in the dark. The bed holds you, the room is quiet, you are safe here, and the universe is enormous and ancient and still telling its story all around you. Stars are born inside clouds of gas and dust, enormous structures called molecular clouds that drift through the spaces between stars. Some of these clouds are hundreds of light years across, so large that light itself takes centuries to cross them. Inside these clouds, gravity does its quiet work, pulling gas together, compressing it, heating it, until the pressure and temperature at the center become so extreme that hydrogen atoms begin to fuse together, forming helium and releasing an extraordinary amount of energy in the process. That energy is what we call starlight, and it is what makes the Stelliferous Era so beautiful. It is the age when matter has learned to shine. But here is the thing that makes this story a sleep story, a lullaby story. The Stelliferous Era will not last forever. Stars need fuel. They burn hydrogen the way a candle burns wax. And just like a candle, when the fuel runs out, the flame dies. The most massive stars, the blue giants and the supergiants, they burn brightest, but they also burn fastest. A star 10 times the mass of our sun might live for only 20 million years, which sounds like a long time, but in cosmic terms, it is a blink. Our sun is a middleweight star, a yellow dwarf, and it has enough fuel to burn for about 10 billion years total. It is currently about halfway through its life, roughly 4.6 billion years old, with another 5 billion or so to go. But the real survivors, the patient ones, the ones who will witness more of the universe's story than any other kind of star, are the red dwarfs. Breathe in and out. Let your body sink a little deeper. You do not need to hold yourself up. You are held. Red dwarfs are small, cool, and incredibly dim. The smallest of them are barely larger than Jupiter, and they give off so little light that not a single red dwarf in the entire Milky Way is visible to your naked eye from Earth. But what they lack in brightness, they make up for in patience. Red dwarfs burn their hydrogen so slowly, so frugally, that some of them will continue shining for trillions of years, not billions, trillions. To understand how long that is, consider this. The universe is currently about 13.8 billion years old. A red dwarf can burn for 10 trillion years. That means the smallest red dwarfs will still be shining long after the universe has aged 1,000 times over from where it is now. They are like patient lanterns set burning at the beginning of a very long night, and they will be the last lights on when everything else has gone dark. And here is another reason red dwarfs are special. They are the most common type of star in the universe by an enormous margin. Roughly 70% of all stars are red dwarfs. If you picked a star at random from the Milky Way, there is a 7 in 10 chance it would be one of these quiet, dim, enduring little fires. The universe is not dominated by the bright and the dramatic. It is dominated by the small and the patient. There may be a lesson in that for all of us. The room is still. The air barely moves. You are resting now, and the universe is resting too, in its own slow way, burning through the last golden hours of its brightest age. But the fuel is running out. New stars are already forming at a slower rate than they once did. The peak of star formation in the universe happened roughly 10 billion years ago. Since then, the rate has been declining. The great clouds of gas that once gave birth to entire generations of stars are being used up or heated so much by the stars around them that they can no longer collapse. It is like an autumn that the universe does not notice because it happens so slowly over billions of years. But it is happening. The leaves are changing, the nights are getting longer, and one day the last leaf will fall. In about 100 trillion years from now, the last star will be born. 100 trillion years, that is 100,000 billion years. It is roughly 7,000 times longer than the universe has existed so far, a span of time so vast that human language was not designed to hold it. But it is not infinite, it has an end. The last cloud of gas will collapse, the last faint red dwarf will sputter to life, a tiny dim glow in an ocean of darkness, and after that, no new star will ever form again. The universe will still be full of stars for a while after that. The red dwarfs already burning will continue for trillions of years more, but no new ones will join them. The population will only shrink, never grow. And as each red dwarf exhausts the last of its hydrogen, it will cool and dim and fade until it is nothing more than a tiny dark sphere drifting through empty space. One by one, across the entire cosmos, the lights will go out. Not with explosions, not with drama, just a slow, quiet dimming, like candles at the end of a very long evening, their wicks burning down to nothing, their flames shrinking, wavering, and then going still. In and out. Your eyelids may feel heavier now. That is fine. You do not need to keep them open. You do not need to see anything. The story will continue even if you close your eyes, even if you fall asleep, because the universe tells its stories to sleeping ears just as willingly as to waking ones. And when the last red dwarf goes dark, the Stelliferous Era will be over. The universe will never be bright again, not in the way it is now, not with that generous, radiant, warming light that stars provide. The age of light will be finished. And what comes next is something quieter still. To understand what happens after the stars are gone, you need to understand a simple idea, one of the most important ideas in all of science, the idea of entropy. Entropy is not a complicated thing, despite how it might sound. Think of it as a calm tendency toward balance, a quiet drift toward equilibrium. If you put an ice cube in a glass of warm water, the ice melts and the water cools until the whole glass is the same temperature. The hot does not get hotter, and the cold does not get colder. Instead, they meet in the middle, they balance out. That is entropy, the tendency of energy to spread out evenly, to move from where it is concentrated to where it is not, until everything is the same. Stars are like tiny pockets of concentrated energy, surrounded by the cold emptiness of space, and all their light, all their heat, is energy flowing outward, spreading, diffusing, moving from hot to cold, from bright to dark. Every photon of starlight that reaches your eye has carried energy from a place where it was concentrated, the star's core, to a place where it was not, the vast empty space between galaxies. And when all the energy has been spread out, when there are no more hot spots or cold spots, no more bright places or dark places, when the entire universe is the same temperature, the same energy density, the same everything, everywhere, then nothing can happen anymore. Because everything that happens, every process, every reaction, every movement requires a difference in energy from one place to another. Hot flows to cold. That is what drives engines and weather and stars and life itself. When there are no more differences, there is no more flow, and when there is no more flow, there is no more change. That is the heat death, not a death by burning, but a death by balance, by evenness, by the universe reaching a state so perfectly uniform that nothing can ever disturb it again. The bed is holding you. You are warm and safe and still, and entropy is doing its gentle work everywhere all the time, spreading warmth from your body into the air, spreading the heat of the day into the cool of the night, always smoothing, always balancing, always tending toward quiet. Entropy is not your enemy. It is the universe's way of finding peace. And now, let us drift into the next chapter of the story, the era that follows the death of the last star. After the Stelliferous Era ends, after the last red dwarf has cooled and gone dark, the universe enters a long, dim, patient chapter that scientists call the Degenerate Era. The name sounds harsh, but in physics, the word degenerate simply describes matter that has been compressed into unusual states, matter that follows different rules than the matter you encounter in everyday life. In the Degenerate Era, the universe is not empty, it is full of remnants, the leftovers of all the stars that once burned. White dwarfs are everywhere, the dense, compact cores left behind when stars like our Sun reach the end of their lives. A white dwarf is roughly the size of the Earth, but it contains as much mass as the Sun. A single teaspoon of white dwarf material would weigh about 5 tons, as much as a large elephant compressed into the size of a sugar cube. These white dwarfs are no longer generating energy through fusion. Their nuclear fires went out long ago, but they are still warm, still glowing faintly with the leftover heat from billions of years of burning. Think of them as porcelain moons, pale and smooth and slowly cooling, drifting through the dark like embers carried on an invisible breeze. In and out, you are drifting too, gently, slowly, carried by the rhythm of your own breath. Over trillions and trillions of years, the white dwarfs will cool. They will radiate away their heat, degree by degree, century by century, growing dimmer and colder, their surfaces darkening from white to yellow to red to a deep, barely visible, infrared glow. And eventually, after a span of time so long that the word trillion begins to feel small, they will reach the same temperature as the space around them, and they will stop glowing entirely, becoming black dwarfs, cold, dark, invisible spheres of incredibly dense matter drifting forever through the void. No black dwarf has ever existed because the universe is not yet old enough for any white dwarf to have cooled completely. It takes far longer than 13.8 billion years. It takes quadrillions of years or more. But one day, every white dwarf in the universe will become a black dwarf, and the faint glow of the Degenerate Era will fade to nothing. The room around you is quiet, so quiet you can hear your own heartbeat if you listen, and the universe in the Degenerate Era is quieter still, a vast empty space populated only by invisible remnants, drifting, cooling, waiting. Neutron stars are there too, the collapsed cores of stars much more massive than our sun, objects so dense that a sugar cube of neutron star material would weigh roughly 1 billion tons. These are the densest objects that exist outside of black holes. When they are young, neutron stars spin incredibly fast, some of them rotating hundreds of times per second, sending beams of radiation sweeping across the sky like cosmic lighthouses. But by the time the Degenerate Era arrives, they have slowed down, their magnetic fields have weakened, their beams have faded. They are still there, still spinning, but barely, like a top that was set going billions of years ago and is now wobbling almost to a stop. And scattered throughout this dark, quiet universe, brown dwarfs drift as well, objects that were never quite massive enough to ignite nuclear fusion, failed stars, gas giants too large to be planets but too small to be stars. They generate no light of their own. They simply float, cold and silent and alone. Very rarely, over the course of trillions of years, two brown dwarfs might happen to wander close enough to each other that their combined mass ignites a brief flash of fusion, a tiny spark in an ocean of darkness, a star born from collision rather than from a cloud. These events would be extraordinarily rare, perhaps once every trillion years across the entire observable universe. A brief flicker, a small warm glow, and then darkness again. Let your body sink, let your thoughts become lighter, like clouds thinning in a vast sky. You do not need to hold on to any of this. The universe does not need you to remember, it only needs you to rest. And now, deep within the Degenerate Era, something even stranger may begin to happen. Something so slow it makes the cooling of white dwarfs look sudden by comparison. Protons may decay. A proton is one of the fundamental building blocks of matter. Every atom in your body, every atom in the earth, in the stars, in everything solid or liquid or gas that has ever existed, contains protons at its core. Protons are incredibly stable. No one has ever observed a proton decaying, and current experiments suggest that if it happens at all, it takes at least 10 to the power of 34 years. That is a 1 followed by 34 zeros. Some theories suggest the timescale might be even longer, 10 to the power of 40 years or more. But in the Degenerate Era, time is the one thing the universe has in unlimited supply. If protons do decay, then over these unimaginable spans of time, every piece of ordinary matter in the universe will slowly dissolve. Atom by atom, the white dwarfs will crumble, the neutron stars will disintegrate, the brown dwarfs will evaporate into a thin mist of subatomic particles. Everything solid, everything you have ever touched or stood upon or held in your hands will gradually unmake itself, not through violence or destruction, but through the patient, quiet ticking of a clock that counts in increments too large for the human mind to hold. In and out, the pillow holds your head, the blanket holds your warmth. You are safe, and the universe is patient, and everything in time finds finds its way to stillness. After the protons have decayed, after the last white dwarf has dissolved into a mist of electrons and photons and neutrinos, the Degenerate Era comes to an end, and the universe passes into its next great chapter, the age of the last remaining structures, the Black Hole Era. Let us linger a while longer in the age of stars, because there is so much beauty here, and beauty should not be rushed, especially when you are drifting towards sleep. If you look up at the night sky on a clear evening, far from city lights, you see something extraordinary. You see time itself. The light from the nearest star beyond our sun, a red dwarf called Proxima Centauri, has been traveling for 4.2 years to reach your eyes. When you look at it, you are seeing it as it was 4 years ago. The light from Sirius, the brightest star in the night sky, has been traveling for 8.6 years. The light from Vega, about 25 years. The light from Polaris, the North Star, has been traveling for roughly 430 years. When you look at Polaris, you are seeing light that left that star when Shakespeare was alive. And the faint smudge of the Andromeda Galaxy, visible on a very dark night, that light has been traveling for 2.5 million years. When that light began its journey, your ancestors were walking the plains of Africa and learning to shape the first stone tools. The night sky is a time machine. Every point of light is a message from the past, some recent, some ancient, all arriving together on the same dark canvas, creating the illusion of a single moment, when in reality you are seeing millions of different moments layered on top of each other. The bed holds you, the room is dark and still, and outside, whether you can see them or not, the stars are sending their ancient light toward you, patient and steady and old beyond imagining. Now let us visit a place where new stars are being born right now as you listen. The Orion Nebula, a vast cloud of gas and dust, sits about 1,344 light-years from Earth in the constellation of Orion. You can see it with the naked eye as a faint fuzzy patch in the middle of Orion's sword. Inside this cloud, gravity is pulling gas together, compressing it into dense knots called protostars. Each protostar is surrounded by a swirling disk of gas and dust from which planets will eventually form. Some of these protostars will become massive blue-white stars that will burn fiercely and die young. Some will become stable yellow stars like our Sun, and many, most of them, will become red dwarfs, those quiet, patient lanterns that will burn for trillions of years. Right now, as you rest, new stars are igniting inside the Orion Nebula. New fusion cores are sparking to life. New light is being born. It is happening slowly by human standards, over thousands and millions of years, but it is happening. The universe is still creating, still building, still lighting its candles, even as the long night ahead draws slowly closer. In and out. Let that knowledge be a comfort. The stars are being born, and you are here to witness the age in which it happens. Many stars do not live alone. In fact, roughly half of all stars exist in binary systems, pairs of stars that orbit each other, bound together by gravity, dancing in slow circles around a shared center of mass. Some binary pairs are wide, the two stars separated by hundreds of astronomical units, barely aware of each other's presence. circling lazily over thousands of years. Others are close, so close that their surfaces nearly touch, so close that matter flows from one star to the other in thin, hot streams, creating patterns of light and shadow and energy exchange that are among the most intricate in nature. And when one star in a close binary dies before the other, the results can be dramatic. A white dwarf pulling matter from a still living companion, accumulating hydrogen on its surface until the pressure triggers a thermonuclear explosion, a nova, a brief bright flash that can make the system temporarily visible from thousands of light years away. And in some cases, when a white dwarf accumulates too much mass, it crosses a critical threshold about 1.4 times the mass of our Sun, called the Chandrasekhar limit, and the entire star detonates in a Type 1a supernova, one of the most energetic events in the cosmos, an explosion so uniform and so bright that astronomers use it as a standard candle to measure distances across the universe. It was exactly these Type 1a supernovae that led to the discovery in 1998 that the expansion of the universe is accelerating, a discovery that earned the Nobel Prize, and that has profound implications for how the heat death will ultimately unfold. But that is a thought for another moment. For now, let your mind rest on the image of two stars, circling each other, slowly, patiently, in the dark, like two dancers who have been waltzing for 1 billion years and show no sign of stopping. The room is quiet, the air is warm and still, your breathing has settled into its own slow rhythm, and you are drifting gently, the way light drifts through space, unhurried, unforced, simply moving toward wherever the quiet takes it. Let us think for a moment about the lives of the biggest stars, the ones that live fast and die spectacular deaths. When a massive star, one with 8 or more times the mass of our Sun, reaches the end of its life, it does not simply cool and fade. It goes through a dramatic sequence of events that takes only a few million years from start to finish. First, it burns through its hydrogen, fusing it into helium in its core. This takes most of its life, millions of years. Then the hydrogen runs out, and the core contracts and heats up until it is hot enough to start fusing helium into carbon and oxygen. This stage is shorter, hundreds of thousands of years. Then the helium runs out, and the core contracts again, and begins fusing carbon into neon and magnesium. This takes perhaps 1,000 years. Then neon fuses into oxygen and magnesium in about a year. Then oxygen fuses into silicon and sulfur in about 6 months. And finally, silicon fuses into iron in about 1 day. 1 day, after millions of years of burning, the last stage takes just 24 hours. And then everything stops, because iron is the end of the line. Fusing iron does not release energy, it absorbs energy. The core suddenly has no way to support itself against its own gravity. In less than a second, the core collapses. The outer layers come crashing inward at 1/4 of the speed of light. They hit the incompressible core and bounce, and a shock wave rips outward through the star, tearing it apart from the inside out. This is a core collapse supernova, and for a few weeks, The dying star outshines everything else in its galaxy. The explosion scatters heavy elements into space: gold, silver, platinum, uranium, elements that could only have been forged in the extreme conditions of a supernova, elements that will drift through space for millions of years before being incorporated into new stars, new planets, new worlds, new you. Every atom of gold in every ring on every hand on Earth was created in a supernova, or possibly in the collision of two neutron stars. Every atom of calcium in your bones, every atom of iron in your blood, was forged inside a star that died before our sun was born. You are stardust, and that is not a metaphor. It is a literal scientific fact. You are made of materials that were once inside stars, materials that have been recycled through the cosmos multiple times over billions of years. In and out, the stardust breathes, the stardust rests, the stardust listens to a story about the fate of all the stars that made it. Now, there is a beautiful diagram in astronomy called the Hertzsprung-Russell diagram. You do not need to remember the name, but the idea behind it is lovely. It is simply a chart that plots stars according to their brightness and their surface temperature, and when you plot thousands of stars on this chart, a pattern emerges. Most stars fall along a diagonal band called the main sequence, which runs from the hot bright blue stars in the upper left to the cool dim red stars in the lower right. Our sun sits roughly in the middle of the main sequence, not too hot, not too cool, not too bright, not too dim, an ordinary star in an ordinary position on an ordinary diagram. And the red dwarfs sit at the bottom right, the coolest, the dimmest, the longest lived. They are the quiet majority, the wallflowers of the stellar party, barely noticed, but always there. As the Stelliferous Era progresses and the massive hot stars die off one by one, the main sequence will gradually empty from the top down. The blue giants go first, then the white stars, then the yellow stars like our sun, until only the red dwarfs remain, a crowd of tiny dim lanterns in an otherwise dark universe. The Hertzsprung-Russell diagram of the far future will show only a small cluster of dots in the lower right corner, the last embers, the last warmth, the last defiance against the cold. And eventually, even those dots will wink out. The blanket is warm, the pillow is soft, your body is heavy with rest, and the universe is patient, so patient, willing to wait trillions of years for the last candle to burn down to nothing. Let us turn our attention now to a star that you know well, even if you have never thought about it in quite this way. Our sun. Our sun is 4.6 billion years old, and it has approximately 5 billion years of hydrogen fuel remaining in its core. That means it is roughly halfway through its life, a middle-aged star, steady and reliable. But it will not always be this way. In about 1 billion years, the sun will be roughly 10% brighter than it is today, which will significantly increase the temperature on Earth. The oceans may begin to evaporate, the climate will shift. In about 5 billion years, the sun will exhaust the hydrogen in its core, and it will begin to change. The core will contract and heat up, while the outer layers expand. The sun will swell into a red giant, growing so large that it will swallow the orbits of Mercury and Venus, and possibly Earth as well. 100 million years or so, the red giant sun will burn helium in its core, creating carbon and oxygen before shedding its outer layers in a beautiful expanding shell of gas called a planetary nebula. The core will be left behind as a white dwarf, a sphere roughly the size of the Earth, but containing more than half the sun's original mass. This white dwarf will glow white hot at first, then slowly cool over billions and trillions of years, growing dimmer and redder and colder until it fades to black. That is the fate of our sun, and the fate of roughly 97% of all stars in the Milky Way. They are not massive enough to explode as supernovae. They simply swell, shed, collapse, and cool. Quietly, the way most lives end, not with drama, but with a gradual settling, a slow exhale, a gentle dimming of the light. In and out. You are safe. The sun has 5 billion years of burning left. 5 billion years is an almost unimaginable span of time, more than enough for a good night's sleep and a good morning after it. Rest now, and let the stars take care of themselves. They have been doing it for 13.8 billion years without your help. They will manage a few hours more, and so the universe drifts onward through the Stelliferous Era, still burning, still shining, still radiating warmth into the void. But you might wonder, where does all that warmth go? All the light that every star has ever radiated, every photon that has ever left the surface of a sun, where does it end up? The answer is, it spreads out, it disperses. It travels through space at the speed of light, and as space itself expands, the photons get stretched, their wavelengths grow longer, their energy decreases. A photon of visible light emitted by a star billions of years ago will eventually be stretched into an infrared photon, then a microwave photon, then a radio wave, each transition representing less and less energy, less and less warmth. This is what the expansion of the universe does to light. It redshifts it, pulls it toward longer and longer wavelengths, like stretching a rubber band until it becomes thin and weak. The cosmic microwave background radiation, that faint glow that fills all of space, is the stretched remnant of the very first light the universe ever produced. It was once as hot and bright as the surface of a star, but 13.8 billion years of expansion have cooled it to just 2.7 degrees above absolute zero, a whisper of warmth in a very cold cosmos. The bed is warm beneath you, the air around you is gentle, your own body radiates heat quietly, steadily, like a tiny star in its own right, a warm presence in a cool room, and the entropy of the room increases very slightly with every breath you take, every calorie of heat your body releases. You are a participant in the second law right now, in the most gentle and natural way possible. Let us think a little more about the second law of thermodynamics, because it is the true engine of this entire story, the invisible force that drives the universe from brightness to darkness, from complexity to simplicity, from the Big Bang to the heat death. The second law says that in any closed system, the total entropy can only stay the same or increase. It can never decrease on its own. But what does that really mean, in a way that a 16-year-old lying in bed could understand? Imagine Imagine a room with a hot cup of tea on one side and a cold glass of water on the other. The room has a difference, a gradient, heat here, coolness there. Over time, the tea cools and the cold water warms, until eventually the whole room is the same temperature. The difference has been erased, the gradient has been smoothed out. That smoothing, that erasing of differences, is entropy increasing. Now imagine the entire universe as that room. Stars are the hot cups of tea, space is the cold water, and the light radiating from stars into space is the heat flowing from hot to cold. Eventually, given enough time, all the tea will cool, all the stars will go out, and the entire room, the entire universe, will be the same temperature everywhere. No more gradients, no more differences, no more flow. That is the heat death. It is not death by fire, it is death by balance, by equilibrium, by the universe finally achieving the most even, most uniform, most peaceful distribution of energy possible. In and out, your breathing is a rhythm, a pattern, a small, predictable wave moving through you, and each wave carries you a little deeper into rest. Now let us think about the stars one more time, because the stars are the heroes of this story, and they deserve a long and loving farewell. There are many kinds of stars, and each one has its own personality, its own lifespan, its own way of dying. The most massive stars, the blue supergiants and hypergiants, are the divas of the cosmos. They burn with extraordinary brilliance, tens of thousands of times brighter than our sun, their surfaces blazing at temperatures of 30,000 degrees or more. But they pay for that brilliance with brevity. A blue hypergiant might burn through its entire fuel supply in just a few million years, and when the fuel runs out, the star dies in one of the most spectacular events in nature, a supernova. In a single second, the star's core collapses, and the outer layers are blasted outward at a significant fraction of the speed of light. For a few weeks, the supernova can outshine an entire galaxy, billions of stars, all eclipsed by the death of one. Supernovae are beautiful, but they are also brief. They are the fireworks of the cosmos, bright and loud, and then gone. Stars like our sun are more moderate. They burn for about 10 billion years, and when their fuel runs out, they swell into red giants, shedding their outer layers in vast glowing shells called planetary nebulae before collapsing down to white dwarfs, those dense porcelain moons we spoke of earlier. But the red dwarfs, the patient lanterns, they are the ones that matter most to this story, because they will be the last. The room is quiet, the house is quiet, the street outside is quiet, and you are quiet too, inside and out, resting in the gentle dark, while the universe burns on and on and on for now. Red dwarfs are remarkable for their efficiency, unlike our sun, which burns hydrogen only in its core, leaving the hydrogen in its outer layers untouched. A red dwarf is fully convective. That means the gas inside a red dwarf circulates from top to bottom and back again, like a pot of soup on a very low flame, constantly stirring itself, bringing fresh hydrogen down to the core and carrying spent helium back up. This means a red dwarf can burn almost all of its hydrogen, not just the portion in its core. It wastes almost nothing. Our sun will use only about 10% of its total hydrogen before it dies. A red dwarf will use nearly all of it. This is why red dwarfs can burn for so extraordinarily long. They are not brighter or bigger or more powerful. They are simply more careful, more patient, more thorough. The smallest red dwarfs, with about 8% of the sun's mass, which is barely enough to sustain fusion at all, will burn for roughly 10 trillion years. 10 trillion years. The universe is 13.8 billion years old. That is less than 1% of the lifespan of the smallest red dwarf. We are at the very beginning of the age of these patient little stars. They have barely started. And when a red dwarf finally does exhaust its hydrogen, after trillions of years of quiet burning, it does not explode. It does not swell into a red giant. It simply cools. It becomes a helium-white dwarf, a tiny dense sphere of helium, slowly radiating its remaining heat into the void, fading, dimming, over more trillions of years, until it becomes a dark, cold cinder, drifting silently through space. There is something deeply calming about the red dwarfs. They do not demand attention. They do not announce themselves. They simply burn quietly, steadily, for an almost unimaginable length of time, and then they rest. Perhaps you can learn something from them tonight. The art of quiet endurance, the beauty of not rushing, the peace of burning slowly and steadily rather than brightly and briefly. In and out. Your body is a kind of star too, burning food for energy, radiating warmth into the room. And tonight, you are banking your fires, dimming your light, letting yourself cool gently towards sleep, exactly as the universe itself will one day cool towards stillness. Let us drift a little further into the future now, past the last red dwarf, into the early stages of the Degenerate Era, where the universe begins to change in ways that are harder to imagine. In the early Degenerate Era, the universe is not completely dark, not yet. White dwarfs are still glowing, faintly. Their surfaces are cooling from thousands of degrees to hundreds, to tens, to single digits above absolute zero, but they have not gone fully dark yet. If you could somehow be present in the early Degenerate Era, and if your eyes could see infrared light, you would see the remnants of galaxies as collections of dim, warm points, like a city seen from far away after most of the lights have been switched off. A few still glow, but most of the windows are dark. The shape of the galaxies would be different too. Over trillions of years, the stars within galaxies scatter each other through gravitational encounters. Some stars are flung outward, ejected into intergalactic space, while others drift inward toward the central black hole. Slowly, very slowly, the galaxies dissolve. They do not explode or fly apart. They simply unravel, star by star, like a sweater pulled thread by thread until nothing remains. About 90% of the stellar remnants in a galaxy will eventually be ejected into the void, scattered across millions of light years of empty space, drifting alone, cooling alone, with no companion and no destination. The remaining 10% will spiral inward and be consumed by the central supermassive black hole, feeding it, adding to its mass, making it slightly larger for the long vigil it will keep in the black hole era. The blanket is warm, the pillow is soft, Your eyelids are heavy, and that is fine. Let them close if they have not already. The story will continue in the dark behind your eyes, in the quiet theater of your imagination, where the universe plays its longest scenes. During the Degenerate Era, something else is happening too, something that involves the very fabric of matter itself. We spoke earlier about proton decay, the possibility that the protons at the heart of every atom might be unstable over extremely long timescales. Let us explore that idea a little more deeply, because it is one of the strangest and most profound predictions in all of physics. In your everyday experience, matter seems permanent. A rock stays a rock, a mountain stays a mountain, an iron atom stays an iron atom for as long as you could ever care to watch. But some theories of particle physics, called grand unified theories, predict that protons are not truly stable. They are simply very, very long-lived. A proton might last for 10 to the power of 36 years before decaying, or perhaps 10 to the power of 41 years, or perhaps even longer. The exact number depends on which theory is correct, and we do not yet know which one is. But even the most conservative estimates give a proton a lifespan far shorter than the age of the Dark Era, which means that if proton decay happens at all, it will have plenty of time to dismantle every atom in the universe. Think of what that means. Every white dwarf made of carbon and oxygen, each carbon atom containing 6 protons and 6 neutrons, each oxygen atom containing 8 protons and 8 neutrons, over the span of 10 to the power of 40 years, every single one of those protons will decay. The proton splits into lighter particles, positrons, pions, photons. The atom comes apart. The crystal structure of the white dwarf crumbles, not because of any external force, but because the building blocks themselves are dissolving from within. It is like a sandcastle made of sand grains that are each slowly evaporating, one by one, over aeons, until the castle is just a memory and a faint glow of scattered light. In and out. Do not worry about any of this. It is only a story, a very long story about very distant things, and you are here, warm and safe and present, in the golden age of the cosmos, surrounded by stable atoms and steady light. If proton decay does happen, then by the end of the Degenerate Era, all ordinary matter in the universe will have been converted into a thin mist of fundamental particles, electrons, positrons, neutrinos, and photons. No more white dwarfs, no more neutron stars, no more brown dwarfs, no more solid anything. The universe will contain only black holes and a diffuse cloud of elementary particles so spread out that any 2 particles might be millions of light years apart. And then the black hole era truly begins. We have already spoken about black holes and Hawking radiation, but let us return to them now with fresher eyes, the way a dreamer might return to a place they visited earlier in the night and see it differently. In the black hole era, the supermassive black holes are not merely large objects. They are the only objects. They are all that remains of the great galaxies that once contained hundreds of billions of stars. The Milky Way's black hole, Sagittarius A star, will by this time have consumed all the stellar remnants that spiraled inward during the Degenerate Era. It will have grown larger, perhaps perhaps tens of millions of solar masses, but it will still be tiny compared to the void around it. A supermassive black hole with 10 million solar masses has an event horizon about 30 million kilometers across. That sounds large, but it is only about a fifth of the distance from the Earth to the Sun. It is a pebble floating in an ocean that stretches for billions of light years in every direction. And that pebble is slowly evaporating. Hawking radiation is the most patient force in the universe. It strips mass from a black hole one particle at a time, and it does so with such excruciating slowness that the entire history of the universe so far, from the Big Bang to this very moment, would not be enough time to notice any change at all. But in the black hole era, time is abundant. Time is the one resource the universe will never run out of. And so the black holes shrink, imperceptibly at first, then faster and faster as they grow smaller, because smaller black holes are hotter and radiate more intensely. It is a beautiful irony. The closer a black hole comes to death, the brighter it shines. Its Hawking radiation grows more energetic. Its temperature rises, its glow intensifies, until in its final moments it burns with extraordinary heat. The last seconds of a black hole's life are violent and radiant, a burst of gamma rays and fundamental particles spraying outward in all directions, the black hole's dying breath, the energy of millions of years of patient evaporation released in a single flash. And then silence. The room is silent around you. The story is quieting. The universe is quieting. Everything is moving toward the same gentle destination. After each black hole evaporates, there is a brief moment of light, a flash, and then darkness again, and the remaining black holes continue their slow vigil, each one unaware that it is one fewer, each one burning through its mass one quantum at a time. The last black hole to evaporate will be the most massive one that ever existed. We do not know exactly which one that will be, or how massive it will have grown, but current estimates suggest it might contain somewhere between 10 billion and 100 billion solar masses. A black hole that size would take approximately 10 to the power of 106 years to evaporate, a number that is 1,000,000 times larger than a Google. When it finally vanishes, it will be the last event of any significance that the universe will ever experience. The last flash of light in the last corner of the cosmos, and then stillness. In and out, you are very close to sleep now, or perhaps you are already there, drifting in and out of awareness, catching phrases and letting them go, like catching snowflakes on your palm and watching them melt. It does not matter which words you hear and which ones you miss. The story is not a test. It is a lullaby, and lullabies work best when you stop trying to follow them and simply let them hold you. And now let us return one more time to the second law, the quiet engine that drives this whole story. The second law of thermodynamics is sometimes described as the most pessimistic law in physics because it guarantees that all ordered structures will eventually break down, that all energy will eventually spread out, that all warmth will eventually cool. But there is another way to see it, a gentler way. The second law is not about destruction, it is about sharing. Energy spreads out because it is moving from places where there is more to places where there is less. It is leveling the playing field. It is smoothing out inequalities. It is finding balance. A star shines because it has more energy than the space around it, and the second law says that energy must be shared. So the star radiates. It gives its energy away, photon by photon, generously, endlessly, until it has given everything it has. The heat death of the universe is what happens when all the giving is done, when every star has shared every photon, when every hot thing has warmed every cold thing, when the cosmic ledger is finally balanced. It is not a tragedy. It is the completion of the universe's longest act of generosity. The bed holds you. You are giving your warmth to the room, your tension to the mattress, your thoughts to the quiet, and in return, the quiet gives you rest. That is the second law at work, right here, right now, in the most personal and gentle way possible. Let us think about one more thing before we move toward the end of our journey together. Let us think about how vast the Dark Era is compared to everything that came before. If you were to represent the entire history of the universe as a single line drawn on a piece of paper, with the Big Bang at one end and the evaporation of the last black hole at the other, and if you made the line 1 meter long, then everything that has happened so far, the entire 13.8 billion year history of the universe, from the Big Bang to the formation of galaxies, to the birth of our sun, to the evolution of life on Earth, to this very night, would occupy a segment so small that you could not see it with the naked eye. It would be far thinner than the width of a single atom. The entire Stelliferous Era, all 100 trillion years of it, would be a slightly thicker mark, but still far too small to see without a powerful microscope. The Degenerate Era would be a bit longer, but still microscopic. And the Black Hole Era, with its Google years of patient evaporation, would occupy nearly the entire line, stretching from one end of the meter to very nearly the other. And the Dark Era, the true Dark Era, the time after the last black hole, would not fit on the line at all, because it never ends. It stretches on and on and on, past the edge of the paper, past the edge of the table, past the walls of the room, past the Earth, past the solar system, past the galaxy, forever. The part of the universe's history that contains stars and light and warmth and life is an unimaginably tiny fraction of the whole, a brief, bright flash at the very beginning of a story that is almost entirely dark and quiet. And you are in that flash right now. You are in the bright part, the warm part, the part where things happen and matter shines and minds can wonder about what comes next. You are alive in the most interesting moment in the entire future timeline of the cosmos. Let that thought be a comfort, not a pressure. You do not need to make the most of it tonight. You just need to rest. The bright flash of the Stelliferous Era will still be here tomorrow when you wake up. The stars will still be burning. The sun will still be shining. The universe will still be young and generous and full of light. In and out. Nothing to do but rest. There are some cosmos that are worth knowing, even at the edge of sleep, even when your mind is barely holding on to the thread of the story. The age of the universe, 13.8 billion years, is measured by the afterglow of the Big Bang, that faint microwave hum that fills all of space, the cosmic microwave background, the oldest light in existence. That light was released when the universe was only 380,000 years old, when it cooled enough for the first atoms to form, and light could travel freely for the first time. Before that moment, the universe was opaque, a dense, hot fog of particles and radiation, and then the fog cleared, and the universe became transparent, and the first light flew outward in all directions, and it has been traveling ever since. That light is still here. It is everywhere. It fills every cubic centimeter of space. You are bathed in it right now, ancient photons from the dawn of time washing over your body at the speed of light, carrying the temperature of a universe that is 2.7 degrees above absolute zero. You cannot feel it. It is far too faint and far too cold, but it is there, the oldest thing you will ever be in the presence of, older than the stars, older than the galaxies, older than any structure in the cosmos. And in the far future, this ancient light will be stretched even further by the expansion of space, its wavelength growing longer and longer, its energy diminishing until it is indistinguishable from the zero-point fluctuations of the quantum vacuum. The oldest light in the universe will eventually fade into the quantum noise, and the universe will lose its last physical memory of the Big Bang. But that is so far in the future that the numbers do not fit inside human language, so let us not worry about it tonight. In and out. The room is dark and quiet, the air is still, your body is warm and relaxed, your breathing is slow and steady, and the universe is turning around you, slowly, the earth rotating on its axis, carrying you toward dawn, carrying you through the night. You are a passenger on a planet that is traveling at 30 kilometers per second around the sun, and the sun is traveling at 220 kilometers per second around the center of the Milky Way, and the Milky Way is traveling at 600 kilometers per second through the cosmos, pulled by the gravitational attraction of enormous structures far beyond our galaxy. You are moving very fast, right now, faster than any vehicle you have ever ridden in, faster than any aeroplane or rocket, and yet you feel nothing because everything around you is moving at the same speed, and motion is always relative, and in your frame of reference, you are perfectly still, lying in bed, breathing slowly, while the cosmos rushes past outside your window at hundreds of kilometers per second. There is a peace in that, a peace in knowing that you can be moving at extraordinary speed and yet feel completely at rest, that motion and stillness are not opposites but perspectives, that the universe can be rushing and quiet at the same time. In and out. Let us think about the temperature of the universe one more time. At the moment of the Big Bang, the temperature was effectively infinite, or at least so high that our physics breaks down trying to describe it. 1 second after the Big Bang, the temperature was about 10 billion degrees. 3 minutes after the Big Bang, The temperature had dropped to about 1 billion degrees, cool enough for the first atomic nuclei to form. 380,000 years after the Big Bang, the temperature had dropped to about 3,000 degrees, cool enough for the first complete atoms and for light to travel freely. Today, 13.8 billion years later, the temperature of the cosmic microwave background is 2.725 degrees above absolute zero. And in the far future, it will continue to drop, approaching zero, but never quite reaching it asymptotically, like a curve that gets closer and closer to a line but never touches it. The universe is cooling, and it has been cooling since the moment it was born. Every second that passes, the average temperature of the cosmos drops by an almost immeasurably small amount. The cooling is so slow that you would need instruments of extraordinary precision to detect it over a human lifetime. But it is happening, right now, as you breathe, as you rest. The universe is a tiny fraction of a degree cooler than it was when you started listening to this story. And that tiny cooling is part of the great story, part of the long, slow arc from the Big Bang to the heat death, the arc we have been tracing together tonight. You are witnessing it, living inside it, participating in it, simply by being alive, simply by being warm in a cool universe, simply by radiating your own small contribution of heat into the room around you. You are part of the story, and the story is part of you, and neither can exist without the other. In and out. The night is deep, the world is quiet, the story has been told. Rest now. The universe has a long way to go, but you only need to make it to morning. And morning will come, as it always does, as it has for 4.5 billion mornings on this planet, bringing light, bringing warmth, bringing the generous energy of a star that still has 5 billion years of burning left. Sleep well. The cosmos holds you, the stars burn for you, the night is yours. In and out. In and out. Let us drift now into one of the most enchanting details of the Degenerate Era, a detail that sounds like something from a fairy tale but is grounded in real physics. As a white dwarf cools over billions of years, something remarkable happens inside it. The carbon atoms in its core, squeezed by enormous pressure into a crystalline lattice, begin to form a structure that is unmistakably diamond. Not metaphorical diamond, not poetic diamond, actual crystallized carbon in a diamond structure. A lattice of atoms arranged in precisely the same pattern as the gemstone in a ring. In 2004, astronomers discovered a white dwarf about 50 light-years from Earth, designated BPM 37093, that appears to have a crystallized core, a diamond roughly the size of the Earth, floating in space, slowly cooling in the dark. They nicknamed it Lucy after the Beatles' song Lucy in the Sky with Diamonds. Imagine it, a diamond the size of a world, orbiting nothing, radiating the last of its warmth into the void, a jewel with no one to admire it, gleaming faintly in a universe that is growing darker by the aeon. In the Degenerate Era, the universe will be full of these diamond hearts, trillions of them, drifting, cooling, their crystal lattices perfect and silent, porcelain moons made of gemstone, the most beautiful objects in the cosmos and the most unseen. The room holds you, the darkness holds you, and somewhere in the deep future, diamond worlds drift through the dark, holding their beauty for no one and needing no one to hold it for. In and out. There is another kind of remnant in the Degenerate era that deserves our attention, the neutron star. When a star between about 8 and 25 times the mass of our Sun explodes as a supernova, the core that remains is not a white dwarf. It is something far more extreme, a neutron star. A neutron star is what happens when gravity crushes matter so tightly that electrons are pressed into protons, forming neutrons, and the entire core becomes a single enormous ball of neutrons, roughly 20 kilometers across, but containing more mass than the Sun. The density is almost beyond comprehension. A sugar cube of neutron star material would weigh about 1 billion tons, as much as a mountain, compressed into a cube you could hold in your hand, if your hand could survive the experience, which it absolutely could not. When neutron stars are young, they are extraordinary objects. Some of them spin hundreds of times per second, sending beams of radiation sweeping across the sky like cosmic lighthouses. These are pulsars, and their timing is so precise that they rival atomic clocks. They also possess the most powerful magnetic fields in the known universe, trillions of times stronger than a refrigerator magnet, strong enough to distort the shape of atoms, strong enough to be lethal from thousands of kilometers away. But by the Degenerate era, all of that youthful fury will have faded. The magnetic fields will have decayed, weakening over billions of years as the electric currents inside the neutron star slowly dissipate. The rapid spinning will have slowed, the pulsars winding down like tops on a table, turning slower and slower and slower until they barely rotate at all. What remains is a small dark sphere, still incredibly dense, but no longer pulsing, no longer magnetic, no longer announcing its presence to the cosmos, just sitting quietly in the dark, cooling, waiting as the aeons pile up around it like silent snow. Your muscles are soft now, your jaw is loose, your fingers uncurled. Your body is doing what the neutron stars will one day do, slowing down, letting go of its spinning, finding the stillness at the center of everything. In the Degenerate era, pairs of stellar remnants that were once in binary systems will continue to orbit each other, white dwarfs circling white dwarfs, neutron stars circling neutron stars, spiraling slowly inward over trillions of years. As they orbit, they lose energy by emitting gravitational waves, tiny ripples in the fabric of space-time itself, predicted by Einstein in 1915 and first detected directly in 2015 by the LIGO Observatory. Gravitational waves carry energy away from the orbiting pair, and as energy is lost, the orbit shrinks. The two objects spiral closer and closer, moving faster and faster until eventually they collide and merge. Two white dwarfs merging can produce a supernova, a brief bright flash in the eternal dark, visible for weeks to anyone or anything that might still be watching, though by the Degenerate era, there will be no one watching. Two neutron stars merging produce an even more spectacular event, a kilonova, an explosion that creates heavy elements like gold and platinum in quantities that would beggar the imagination, scattered into space in a burst of light and matter. These mergers will happen throughout the Degenerate Era, each one a tiny spark of violence and creation in a universe that has otherwise gone very quiet, but they will become rarer and rarer as the supply of binary remnants dwindles, until finally, even these occasional fireworks cease. In and out. Let us think now about the galaxies themselves and what becomes of them as the eras pass. In the current universe, galaxies are gravitationally bound structures, collections of stars and gas and dark matter held together in vast spinning disks or elliptical clouds. But even galaxies are not eternal. Over the next several billion years, our own Milky Way will collide and merge with the Andromeda Galaxy, our nearest large galactic neighbor, forming a giant elliptical galaxy that astronomers have already nicknamed Milkomeda. This collision will not be violent in the way you might imagine. Stars are so small relative to the distances between them that the two galaxies will pass through each other like two swarms of fireflies. Individual stars are extremely unlikely to collide. Instead, the gravitational interactions between the stars will rearrange their orbits, pulling them into new paths, flinging some outward, drawing others inward. Over billions of years, the merged galaxy will settle into a new shape, a large, quiet elliptical cloud of stars, and then it too will begin to dissolve. As we discussed earlier, gravitational interactions between stars within a galaxy act like a slow shuffling. Over trillions of years, some stars gain energy and are ejected into intergalactic space, while others lose energy and fall toward the center. Eventually, the galaxy evaporates, its stars scattering like seeds blown from a dandelion. Meanwhile, the expansion of the universe is pushing galaxy groups apart from each other faster and faster as dark energy drives the acceleration. In the deep future, each galaxy group will become an island, completely isolated, unable to see or communicate with any other group. The light from distant galaxies will be redshifted beyond detection, stretched to infinite wavelengths, carrying no usable information. If intelligent beings existed in that far future, they would look out at the sky and see nothing but their own galaxy group. They would have no way of knowing that trillions of other galaxies had ever existed. The universe would appear small and empty and alone. The pillow cradles your head, the blanket holds your warmth close. The room is a small island of comfort in the vast dark of the night, and you are safe here, perfectly safe, as the universe outside does whatever the universe does. Now, let us think about dark matter, because dark matter plays a role in this story too, a quiet, supporting role, like a stagehand who never appears in front of the audience, but without whom the show could not go on. Dark matter makes up roughly 85% of all the matter in the universe. It does not emit light, it does not absorb light, it interacts with ordinary matter only through gravity, but its gravitational influence is everywhere. Every galaxy sits inside a vast halo of dark matter, a cloud of invisible particles that extends far beyond the visible edges of the galaxy. It is the dark matter halo that holds the galaxy together, providing the extra gravitational pull that keeps the outer stars from flying off into space. In the Degenerate Era, after the stars have died and the galaxies have begun to dissolve, the dark matter halos will still be there, vast, diffuse, invisible. They will be the last large-scale structures in the universe, apart from the black holes. But even the dark matter halos will eventually dissolve. The same gravitational interactions that scatter stars out of galaxies will gradually disperse the dark matter as well, spreading it ever more thinly across ever more space. And as the universe continues to expand, the dark matter will thin out further and further until it is an almost undetectable mist, a faint presence everywhere and nowhere, a memory of the structures it once held together. In and out. Everything disperses, everything spreads out, everything finds its way to evenness and equilibrium, including you tonight, as the tension in your muscles spreads into the mattress, and the warmth in your body spreads into the room, and the thoughts in your mind spread into the quiet, growing thinner and thinner until they are barely there at all. This is not something to resist, it is something to welcome. The universe has been doing it for 13.8 billion years. This gentle spreading, this calm balancing, it is the most natural process in existence. Let it carry you, black holes. You have heard the name before, perhaps many times, and perhaps you have imagined them as violent things, hungry things, destructive things. But tonight, in the black hole era, they are none of those things. They are the last quiet sentinels of a universe that has run out of almost everything else. A black hole is a region of space where gravity has become so overwhelmingly strong that nothing, not light, not matter, not even information itself, can escape once it crosses a boundary called the event horizon. Think of the event horizon not as a wall, but as a point of no return, like the edge of a waterfall where the current becomes too strong to swim against. Anything that drifts past it drifts inward forever. In the universe you live in now, black holes are formed when the most massive stars die. When a star more than about 25 times the mass of our sun exhausts its fuel, its core collapses under its own gravity. And if the core is massive enough, nothing can stop the collapse. The matter crushes inward and inward and inward, past the density of a white dwarf, past the density of a neutron star, until it occupies a point of essentially infinite density called a singularity. And around that singularity, the event horizon forms, a dark sphere in space, invisible against the blackness, detectable only by the way it bends the light of things behind it. The room is still, your body is heavy and warm. You do not need to picture any of this perfectly, just let the words wash over you, like waves reaching ashore and pulling gently back. In the black hole era, trillions upon trillions of years from now, the stellar mass black holes left behind by dead stars have been drifting through the dark for an almost inconceivable length of time. But the true monarchs of this era are the supermassive black holes, the ones that sit, or rather sat, at the centers of galaxies. Every large galaxy in the current universe has a supermassive black hole at its heart. Our own Milky Way has one called Sagittarius A star, which contains roughly 4 million times the mass of the Sun, compressed into a region smaller than the orbit of Mercury. Other Other galaxies have black holes far more massive still. The black hole at the center of the galaxy Messier 87, the one that was famously photographed in 2019, contains 6.5 billion solar masses. In the black hole era, galaxies no longer exist as we know them. The stars have all gone out long ago. The gas has been used up. The structure of spiral arms and galactic disks has dissolved. But the supermassive black holes remain, sitting in the dark, the last organized structures in the cosmos, like ancient monuments in a desert that has swallowed everything else. They do not shine, they do not burn, they simply persist, patient and vast and silent. In and out, let your breathing become so slow you barely notice it. Let each exhale carry a little more tension out of your body. You are drifting now through the longest night the universe will ever know. And now we come to one of the most remarkable discoveries in the history of physics, a discovery made by a man sitting in a wheelchair in Cambridge, England, in the year 1974. Stephen Hawking asked a question that nobody had thought to ask before. Can a black hole lose mass? The answer, which stunned the scientific world, was yes. Hawking showed that at the very edge of a black hole's event horizon, where the curvature of space-time becomes extreme, something strange happens at the quantum level. In the vacuum of space, which appears to be empty, pairs of particles are constantly flickering into existence, a particle and its antiparticle appearing together for the briefest possible instant and then annihilating each other and vanishing again. This is not a metaphor. It is one of the most well-confirmed predictions of quantum mechanics. The vacuum is not truly empty. It seethes with these ghostly pairs, appearing and disappearing billions of times every second in every tiny patch of space. Normally, these virtual particles have no lasting effect. They appear, they cancel each other out, and the universe moves on. But at the edge of a black hole, right at the event horizon, something different can happen. One particle of the pair can fall into the black hole while the other escapes. The escaping particle carries real energy away from the black hole, and the black hole loses a tiny, infinitesimally tiny amount of mass in the process. This is Hawking radiation, and it is extraordinarily faint, a whisper so quiet that no instrument we have ever built could detect it from a real black hole. For a stellar mass black hole, the temperature of this radiation is a fraction of a billionth of a degree above absolute zero, colder than the cosmic microwave background radiation that fills all of space, colder than almost anything you could imagine. The pillow beneath your head is soft, the blanket is warm, your body is sinking gently into rest, and somewhere in the far, far future, the last black holes are losing mass, one particle at a time. The process is almost incomprehensibly slow. A black hole with the mass of our Sun, roughly 2 × 10 to the power of 30 kilograms, would take approximately 10 to the power of 67 years to evaporate completely through Hawking radiation. That is a 1 followed by 67 zeros, a number so vast that the current age of the universe, 13.8 billion years, is essentially 0 by comparison. And a supermassive black hole, like the one at the center of our galaxy, would take roughly 10 to the power of 100 years to evaporate, a Google years, a 1 followed by 100 zeros. There is no way to hold that number in your mind, and you do not need to try. Just know that it is very, very, very long, longer than any span of time that has ever been or ever will be in the bright parts of the universe's history. But it is not infinite. That is the key. Even a Google years has an end. And when that time is up, the black hole will have shrunk, grown warmer, radiated more and more intensely as it got smaller, until in its final moments it will be very small and very hot, and it will release its last remaining energy in a brief bright flash, like a spark at the end of a very long fuse. And then it will be gone, entirely, completely. Nothing left but a fading puff of radiation dispersing into the void. In and out, the room is dark and still. The world outside is asleep or nearly so, and you are here, warm and safe, listening to the story of the longest goodbye the universe will ever say. One by one, across the entire cosmos, the black holes will evaporate. The small ones go first, the stellar mass remnants, then the intermediate ones, then the large ones, and finally, after a span of time that dwarfs everything that came before, the very last supermassive black hole, the heaviest one that ever formed, will radiate its final particle, grow infinitesimally smaller, and vanish in a tiny flash of light. And with that flash, the last organized structure in the universe will cease to exist. No more stars, no more planets, no more white dwarfs or neutron stars, no more black holes, no more atoms if the protons have decayed, no more anything that you could point to and call a thing. Just particles, scattered, drifting, impossibly far apart, in a space that is still expanding, still stretching, still growing larger. Let your thoughts go quiet now. Let them thin out like stars thinning at the edge of a galaxy, fewer and fewer, dimmer and dimmer, until there is only the dark and your breathing and the warmth of wherever you are resting. The black hole era is over. The Sentinels have stood their watch, and one by one they have dissolved into the night. And the universe enters its final and most enduring chapter, the Dark Era. This is the name scientists have given to the period that follows the evaporation of the last black hole, and it is the longest chapter of the universe's story, not by a small margin, but by an almost infinite one. In the Dark Era, there are no structures of any kind, no objects you could see or touch or stand upon. There are only scattered subatomic particles, photons that have been stretched by the expansion of space until they carry almost no energy at all, neutrinos traveling at nearly the speed of light through absolute emptiness, electrons and positrons drifting so far apart that they will never find each other again. The temperature of the universe is a fraction of a degree above absolute zero, and it is falling, slowly, asymptotically, approaching zero, but never quite reaching it. Nothing happens. That sentence is worth sitting with for a moment. Nothing happens. Not nothing interesting, not nothing dramatic, but literally nothing. No process, no reaction, no change, no event of any kind. because every process requires a difference, a gradient, a reason for energy to flow from one place to another. And in the Dark Era, all differences have been smoothed away, all gradients have been erased, all the energy in the universe has been spread so perfectly, so evenly, across so much space, that there is no longer any reason for anything to move or change or happen. This is maximum entropy, the highest possible disorder, the most even possible distribution of energy. And it is also, in a strange and beautiful way, the most peaceful state the universe can achieve. The bed is holding you, the room is dark, your muscles have softened, your jaw is loose, your hands are open, you are approaching your own kind of equilibrium, a body at rest, a mind at rest, entropy doing its gentle work, smoothing away the tensions of the day. In the Dark Era, time still passes, but it has no markers, no milestones, no way to distinguish one moment from the next. If you were somehow present in the Dark Era, floating in the void, you would have no way to tell whether a second had passed or a billion years, because nothing would have changed in either case. Time without events is time without meaning. It flows, but there is nothing for it to carry. And yet, even in this most absolute of silences, physics has one more surprise. Quantum mechanics tells us that the vacuum of space, even in the Dark Era, is not truly empty. It still shivers with those same quantum fluctuations we mentioned before, those ghostly particle pairs, appearing and vanishing trillions of times per second. Most of the time, these fluctuations are tiny, meaningless. They create a particle and immediately take it back. They are the universe muttering to itself in its sleep. But quantum mechanics also tells us that fluctuations can be of any size. The probability of a large fluctuation is extraordinarily small, vanishingly small, but it is never zero. And in the Dark Era, where time stretches on without limit, even vanishingly small probabilities eventually become certainties. Given enough time, a quantum fluctuation could produce an atom. A longer wait might produce a molecule, an even longer wait, a grain of dust, a rock, a planet. And given truly absurd amounts of time, timescales that make the Google years of black hole evaporation look like the snap of a finger, a quantum fluctuation could theoretically produce a brain. A conscious brain, fully formed, floating alone in the void, with memories that were never lived, thoughts that have no origin, awareness that exists for only an instant before dissolving back into the emptiness from which it came. This is what physicists call a Boltzmann brain, named after the 19th century physicist Ludwig Boltzmann, who first explored the relationship between entropy and probability. It is a strange idea and a deeply unsettling one, and most physicists believe that something in our understanding of cosmology or quantum mechanics must prevent Boltzmann brains from actually forming. But nobody has proven exactly what that something is. You do not need to worry about Boltzmann brains tonight. You are a real brain in a real body, in a real room, with a real blanket and a real pillow and real air filling your real lungs. In and out, in and out. You are here, you are real, and you are safe. There is one more idea that some physicists have explored, an idea that sits right at the edge of what we can currently know. It is called the Poincaré recurrence theorem, and it was first proven by the French mathematician Henri Poincaré in 1890. The theorem says that any system that is confined to a finite space with a finite amount of energy will eventually return to a state very close to its original starting condition if you wait long enough. Applied to the universe, this would mean that if you waited an almost indescribably long time, far, far longer than a Google years, far longer than a Googleplex years, the random quantum fluctuations in the dark era could eventually reproduce something resembling the conditions of the Big Bang. Not the same Big Bang, not our Big Bang, but something similar enough. A sudden concentration of energy, a burst of expansion, a new beginning. Whether this is truly possible depends on questions about the nature of space and time and dark energy that physicists are still working to answer. If space continues to expand forever, if the cosmological constant remains constant, then the conditions for Poincaré recurrence may never be met. But the idea is there, sitting quietly at the horizon of our understanding, a whisper of a possibility that the universe's story might not have a true ending, that it might be a circle rather than a line, or a spiral, or something for which we do not yet have a name. The room is quiet, so quiet. The only sound is your breathing, slow and even and gentle, and perhaps the faintest hum of the world beyond your walls. Let us rest here for a moment at the edge of everything, at the place where the known becomes the unknown, where science meets wonder, where the story of the universe touches the story of sleep. Let us now drift backward, not in time, but in feeling. Let us return to the warmth of the present, to the room you are in, to the body you inhabit, to the breath that moves through you without being asked. You have traveled tonight through the entire future of the cosmos, from the bright, generous age of stars, through the patient dimming of red dwarfs, through the cooling of white dwarfs like porcelain moons, through the slow dissolution of matter itself, through the era of black holes standing sentinel in the dark, through the whisper of Hawking radiation, through the final flash of the last black hole's evaporation, and into the vast, quiet, endless stillness of the dark era. It is a long story, the longest story there is, and it ends not with a bang, but with the most perfect silence imaginable. But here is the thing that makes this story beautiful rather than sad. Right now, in this moment, you are alive. Right now, the stars are burning, the sun is shining on the other side of the earth, or it will be again in a few hours. The Milky Way is turning, slowly, majestically, carrying our solar system along with it. Right now, the universe is in its golden age, its most luminous, most complex, most interesting chapter, and you are here for it. You are made of it. The atoms in your body were forged inside stars that burned and died billions of years before you were born. The carbon in your bones, the iron in your blood, the oxygen you are breathing right now, all of it was cooked in the hearts of ancient stars, scattered into space by supernovae, gathered together by gravity into new clouds, new stars, new planets, and eventually into you. You are not separate from the universe. You are the universe, experiencing itself, thinking about itself, wondering about its own future, and and resting as the universe itself will one day rest. In and out, in and out. The heat death of the universe is not something to fear. It is billions upon billions of years away, so far in the future that the number of years between now and then is larger than the number of atoms in the observable universe. And between now and then, so much will happen. Stars will be born and die. Galaxies will collide and merge. Perhaps civilizations will rise and flourish on worlds we have never seen. Perhaps intelligence will spread across the cosmos in ways we cannot yet imagine. The universe has so much story left to tell, so much light left to give, so much warmth left to share. And right now, tonight, all you need to do is rest. Let the story of the cosmos be your lullaby. Let the patience of the red dwarfs teach you that there is no rush. Let the stillness of the dark era show you that even the universe finds peace. Let the second law of thermodynamics remind you that everything in time settles, smooths, balances, and becomes quiet. You are settling now, smoothing, balancing, becoming quiet. Your breathing is slow, your heart is steady, your body is warm and heavy and still. The stars are burning somewhere above you, even if you cannot see them. They are there, ancient and luminous and patient, the same stars that people have fallen asleep beneath for 100,000 years. And you are here, one more person, in one more night, resting beneath the same vast sky. Let us return now to the black holes, because there is more to their story than we have told, and the deeper you go into this story, the stranger and more wonderful it becomes. When Stephen Hawking first showed that black holes radiate energy and slowly evaporate, it created one of the deepest puzzles in all of physics, a puzzle that remains unsolved to this day. The puzzle is called the black hole information paradox, and it goes something like this. In physics, information is never supposed to be truly destroyed. If you burn a book, the information in the book is not gone, in principle. If you could track every atom of ash and every photon of light and every molecule of gas released by the fire, you could reconstruct the original book. The information has been scrambled, made incredibly hard to read, but it has not been erased. This is a fundamental principle of quantum mechanics. Information is conserved, always. But when something falls into a black hole, what happens to the information it carried? If the black hole then evaporates through Hawking radiation, does the information come back out, or is it lost forever? Hawking's original calculation suggested that Hawking radiation is completely random. It carries no information about what fell into the black hole. It is like the heat rising from a fire, but a fire that produces only generic warmth, no ash, no smoke, nothing you could use to figure out what was burned. If that is true, then information is destroyed when a black hole evaporates, which would violate one of the most fundamental principles in physics. The pillow is cool against your cheek. Your body has settled deeply into the mattress. You do not need to solve this paradox tonight. Nobody has solved it yet, and the finest minds in physics have been working on it for 50 years. You can simply rest with the mystery the way you would rest under a sky full of stars you cannot name. Many solutions have been proposed. Most physicists now believe that the information does come out, encoded in extremely subtle correlations in the Hawking radiation, but the exact mechanism is still debated. One fascinating proposal involves something called the holographic principle, an idea that emerged from the work of Gerard 't Hooft and Leonard Susskind in the 1990s. The holographic principle suggests that all the information contained within a volume of space can be described by data encoded on the boundary of that space, like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. Applied to black holes, this would mean that all the information about everything that has ever fallen into the black hole is encoded on the surface of the event horizon, not inside it. And as the black hole evaporates, this information is gradually released back into the universe. The idea is strange, almost unsettlingly so. It suggests that the three-dimensional space we inhabit might be a kind of projection, a holographic image generated by information stored on a distant boundary. You do not need to understand this. You do not need to believe it or disbelieve it. Just let it sit in your mind like a strange, beautiful dream, a whisper from the edge of what physics can currently say about reality. In and out, the room is still, the world is sleeping, and you are drifting in the company of ideas that live at the very frontier of human understanding. During the black hole era, the supermassive black holes that once anchored galaxies will sometimes encounter each other. When two galaxies merge, their central black holes eventually find each other, drawn together by gravity over millions of years, spiraling inward, closer and closer, emitting gravitational waves of increasing frequency and amplitude. In the final moments before merger, the gravitational waves become so intense that they carry away more energy per second than all the stars in the observable universe combined. This is the most powerful release of energy that can occur in nature, more energetic than a supernova, more energetic than a gamma-ray burst, yet completely invisible to the eye, detectable only by the rippling of space-time itself. And then the two black holes merge, their event horizons touch and blend, and they become a single larger black hole, which rings like a struck bell, vibrating with gravitational waves that gradually dampen as the new black hole settles into its final shape. This process, called a ringdown, produces a specific pattern of gravitational waves that carries information about the mass and spin of the newly formed black hole, a cosmic fingerprint pressed into the fabric of space and time. In the black hole era, these mergers will continue to happen, although less and less frequently, as the remaining black holes drift farther and farther apart in the expanding universe. Eventually, the last merger will occur, two black holes finding each other across an impossibly vast emptiness, circling each other for billions of years, spiraling inward, and finally touching, combining, producing one final ripple in the fabric of reality before the newly merged black hole settles down to begin its own long, slow evaporation. And then there will be no more mergers, because the remaining black holes will be too far apart to ever find each other again. Each one will sit alone in a region of space billions of light years across that contains nothing else, no stars, no planets, no other black holes, Nothing at all except a thin mist of subatomic particles spread so thin it barely qualifies as existing. Imagine the loneliness of the last black hole. It has been sitting in the dark for longer than any number you have ever heard, longer than the age of the current universe multiplied by itself 100 times over. It has watched, if watching is the right word, as every other black hole in the cosmos has evaporated and vanished, one by one, their final flashes growing fainter and fewer, until this one is the only one left. It does not know it is the last. It has no awareness, no mind, no sense of loneliness as we understand it, but there is something poignant about the image nonetheless. The last structured object in the entire universe, the last thing that could be called a thing, sitting in the infinite dark, slowly losing itself, particle by particle, to Hawking radiation. The bed holds you. You are not alone. You are surrounded by air and warmth and the quiet sounds of a world full of other people sleeping, billions of hearts beating in the dark, billions of bodies resting, billions of minds wandering through dreams. You are part of an enormous company of sleepers, and you are welcome among them. In and out. And now let us look more closely at how a black hole dies, not from a distance, but up close, as if we could watch the final moments unfold. For almost all of its existence, a black hole's Hawking radiation is unimaginably faint. The temperature of the radiation is inversely proportional to the black hole's mass, which means that the larger the black hole, the cooler its radiation. A supermassive black hole with 1 billion solar masses has a temperature of about 60 billionths of a billionth of a degree above absolute zero. That is colder than the cosmic microwave background, colder than the void between galaxies, colder than anything you will ever encounter in the real universe. At that temperature, the black hole actually absorbs more energy from the cosmic microwave background than it emits through Hawking radiation, which means it is gaining mass, not losing it. But eventually, as the universe expands and the cosmic microwave background cools further and further toward absolute zero, a crossover point is reached. The black hole's Hawking radiation becomes warmer than its surroundings, and it begins to truly evaporate. The process is agonizingly slow at first. Each particle of Hawking radiation carries away a vanishingly small amount of energy, and the black hole shrinks by an almost immeasurable amount. But as the black hole shrinks, it gets hotter, and as it gets hotter, it radiates faster, and as it radiates faster, it shrinks more quickly, and as it shrinks more quickly, it gets even hotter. This is a runaway process, very, very slow at first, but accelerating gradually over trillions and trillions of years until near the very end, the black hole is shrinking rapidly, glowing brightly, its temperature soaring. In the last second of a black hole's life, it releases a burst of energy equivalent to millions of nuclear weapons. A flash of gamma rays and exotic particles spraying outward in all directions. And then silence. The black hole is gone. The space where it used to be is empty, indistinguishable from the void around it, as if it had never been there at all. All that remains is a fading sphere of radiation, expanding outward at the speed of light, growing dimmer and cooler as it spreads, carrying the last energy the black hole ever possessed, out, 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 into the infinite dark. In and out. You are very deep now, deep in rest, deep in the story, deep in the quiet. Let the words come and go like the hawking radiation itself, faint, patient, carrying just enough warmth to remind you that something is here, that the story is still being told, even as you drift. Let us now explore the deepest and strangest territory of all, the ideas that live at the very edge of what physics can tell us, ideas about the nature of emptiness, the fate of space-time itself, and what it truly means for nothing to happen. In the Dark Era, after the last black hole has evaporated, the universe is almost perfectly empty, but the word almost is doing important work in that sentence. There is a question that physicists have been debating for decades, and it has to do with the nature of the vacuum, the empty space that makes up almost all of the universe. In quantum physics, the vacuum is not truly empty. It is a seething ocean of virtual particles, quantum fields that fluctuate constantly, popping tiny amounts of energy in and out of existence faster than anything can observe. But there is a deeper question. Is our vacuum the lowest possible energy state, or is there an even lower state that the universe has not yet found? If our vacuum is the true vacuum, the absolute lowest energy state, then it will persist forever. The Dark Era will stretch on without end, exactly as we have described. But if our vacuum is a false vacuum, a state that appears stable but is not truly at the lowest possible energy, then something astonishing could happen. The blanket wraps around you, the mattress holds you, your breath moves in and out like a slow, warm tide, and the ideas we are about to explore are so strange and so vast that you can let them wash over you without trying to hold on to any of them. A false vacuum is like a ball resting in a small dip on the side of a hill. It appears stable, it does not move, but it is not at the bottom of the hill. It is only in a local minimum, not a global one. If something nudged the ball hard enough, or if it tunneled through the barrier quantum mechanically, it would roll down to the true bottom and release an enormous amount of energy in the process. If our vacuum is a false vacuum, then a tiny region of space could spontaneously tunnel to the lower energy state, the true vacuum. This would create a bubble of true vacuum that would expand outward at the speed of light, consuming everything in its path. Inside the bubble, the laws of physics might be completely different. Different particles, different forces, different constants, a universe rewritten from the ground up. Everything in the path of the bubble would be destroyed, not destroyed in the sense of being broken apart, but destroyed in the sense of being replaced, overwritten by a new set of physical laws that might not allow for atoms or light or anything recognizable. This is called vacuum decay, and it is one of the most dramatic possible fates for the universe. But here is the comforting thing. If vacuum decay were to happen, you would never know. The bubble expands at the speed of light, which means you cannot see it coming. There is no warning, no time to react, no moment of fear or pain. One instant, the universe is as it is. The next instant, it is something else entirely, and whatever was in the path of the bubble simply ceases to exist as it was. It is the most sudden and complete ending imaginable, and yet it is also the most painless, because pain requires time and vacuum decay gives you none. Most physicists believe that our vacuum is either stable or so long-lived that vacuum decay is not a realistic concern, at least not for many, many, many times the current age of the universe. But the possibility exists, sitting quietly in the equations, like a note written in very small print at the bottom of a very long contract. In and out, the room is warm and still, the walls are solid, the floor is solid, the laws of physics are holding steady, just as they have for 13.8 billion years, and they will almost certainly continue to do so for a very long time to come. You are safe. Tonight, you are safe. Let us set vacuum decay aside and return to the quieter and more likely version of the dark era, the one where the vacuum is stable and the universe simply stretches on forever. In this version of the future, the dark era is a place of almost perfect stillness. The temperature is a tiny fraction above absolute zero. The density of matter is so low that the average distance between any two particles is greater than the diameter of the observable universe today. Nothing happens, not because something is preventing things from happening, but because there is no energy gradient to drive any process, no hot spot to flow toward a cold spot, no concentration of anything that could disperse. It is entropy at its maximum, equilibrium at its most complete, the universe in its most restful possible state. And yet the quantum fluctuations continue. Those tiny shimmerings of the vacuum, virtual particles appearing and disappearing, they never stop because they are a fundamental property of the quantum fields that underlie all of reality. In the dark era, these fluctuations are the only things that happen. They are the universe whispering to itself in its sleep, tiny, meaningless murmurs in an infinite silence. But here is where things become philosophically interesting. If a quantum fluctuation can produce a particle, can it produce two particles? Can it produce an atom? Can it produce a complex structure? In principle, yes. The probability decreases exponentially with the complexity of the structure, but it is never zero. And in the dark era, where time stretches on without limit, even probabilities that are absurdly small will eventually be realized. This is why the idea of Boltzmann brains is so troubling to physicists. If you wait long enough, the random jittering of quantum fields could produce a conscious brain, complete with false memories of a life it never lived, awareness of a universe it has never seen, and the belief that it is a real person in a real world. The probability of this happening at any given moment is so small that it makes the word small seem absurdly inadequate. It is a number with so many zeros after the decimal point that you could not write them all down if you devoted every atom in the universe to storing a single digit. But the dark era has more time than any number can contain, and so, according to the mathematics, it will happen, eventually, given enough eternities. Most physicists find this conclusion disturbing, and many believe it indicates that something is wrong with our understanding of cosmology or quantum mechanics, that some principle we have not yet discovered prevents these fluctuations from growing large enough to produce Boltzmann brains. But nobody has proven what that principle is, and so the question remains open, a a strange loose thread in the fabric of our best theories. Your eyes are closed, or nearly so. Your thoughts are moving slowly, like fish in a deep pond, catching the light for a moment and then sinking back into the dark. You are real. You are here. You are not a Boltzmann brain flickering into existence in the void. You have a past, a family, a body that has lived and grown and carried you through years of real experience. You are anchored in the bright, warm present of the Stelliferous Era, the most real and most vivid chapter of the universe's existence. Rest in that knowledge. Rest in the solidity of the mattress beneath you, the warmth of the air in your lungs, the quiet beat of your heart. These things are real and they are yours. In and out. Now, let us consider what it means for nothing to happen, not as a scientific concept, but as a philosophical one. In the Dark Era, there are no observers, no minds, no instruments, nothing that could experience the passage of time or notice the absence of events. If nothing is happening and no one is there to notice that nothing is happening, is time still passing? This is not a new question. Philosophers have been asking versions of it for thousands of years, but the Dark Era gives it a new and sharper edge, because it describes a state that will last not for a long time, but forever, without interruption, without end, without even the possibility of end. Some physicists argue that time in the Dark Era has no meaning, because time is defined by change, and where there is no change, there is no time. The Dark Era is not an infinitely long period of waiting. It is the absence of periods altogether, a state outside of time, a silence so complete that the concept of duration does not apply. Others argue that time continues to flow whether or not anything happens in it, that the quantum fluctuations, tiny as they are, constitute change, and change constitutes time, and therefore time goes on, ticking away forever in the empty dark. There is no settled answer, and perhaps that is appropriate. Some questions are meant to be held rather than solved, carried gently rather than pinned down, like a firefly cupped in your hands, glowing softly, but lost if you squeeze too tight. The room is very quiet now, the kind of quiet where you can hear the silence itself, a soft background hum of nothing, the kind of quiet that the Dark Era will know, but deeper and longer and more complete. Let the quiet hold you, the way the universe holds its particles, gently, without effort, without expectation, simply holding, because that is what space does. It holds things, even when those things are almost nothing at all. There is one more idea we should visit before we begin our slow return to the present. Some physicists have proposed that the universe may not have a single future, but many, that the laws of physics might allow for multiple outcomes, depending on the behavior of dark energy. If dark energy remains constant, which is the simplest possibility and the one most consistent with current observations, then the universe will expand forever, and the heat death will proceed as we have described, slowly, patiently, reaching maximum entropy over timescales that stretch beyond all counting. But if dark energy increases over time, a scenario called phantom energy, then the expansion of space will accelerate without limit, growing faster and faster until it overcomes not just the gravity holding galaxy clusters together, but the gravity holding galaxies together, then star systems, then planets, then atoms, then subatomic particles, then the fabric of space-time itself. This is called the Big Rip, and it would be a very different kind of ending, not a slow cooling, but a violent tearing, the universe ripping itself apart from the inside out. Current evidence suggests that the Big Rip is unlikely. Dark energy appears to be constant, or very close to it, but we cannot rule it out entirely, and the measurements continue to be refined. And if dark energy were to somehow reverse, to become attractive rather than repulsive, then the expansion of the universe could slow down, stop, and reverse, leading to a collapse, a big crunch, the entire universe falling back in on itself like a deflating balloon, growing hotter and denser until it reaches a state of infinite temperature and infinite density, perhaps triggering a new Big Bang, a new beginning. This cyclic model of the universe, expanding and contracting and expanding again, is one of the most beautiful ideas in cosmology. It suggests that the universe might be eternal in the truest sense, not an infinite line stretching in one direction, but an infinite circle, a rhythm, a cosmic heartbeat. Expand, contract, expand, contract, like breathing, in and out, in and out. We do not know which of these fates awaits the universe, the heat death, the Big Rip, the Big Crunch, or something else entirely that we have not yet imagined. But tonight it does not matter, because all of these endings are so far in the future that the distance between now and then is larger than any number you could write in a lifetime. Tonight, the stars are burning, the universe is warm, life exists, you exist, and you are resting. That is enough, more than enough. It is everything. Let us pause now and rest with the story for a while, not moving forward, not moving backward, just resting here in the middle of the longest tale ever told. Your body is a warm, quiet presence in a dark room, and that is all it needs to be right now. Let your awareness settle into the places where your body touches the bed. Feel the points of contact, the backs of your heels, the weight of your calves, the broadness of your lower back pressing gently downward, the spread of your shoulder blades, the back of your head cradled by the pillow. At each of these points, gravity is doing its work, pulling you gently toward the center of the earth, and the bed is pushing back, holding you up, a perfect balance of forces, equilibrium, the very same equilibrium that the universe itself is slowly drifting toward. Let your awareness move to your hands wherever they are resting. Feel the temperature of the air on your skin, the weight of each finger, the soft curve of your palms. These hands are made of atoms that were forged in stars, carbon and oxygen from a red giant that died 5 billion years ago, calcium from a supernova that lit up a corner of the Milky Way before our sun even existed. Every atom in your body has a history billions of years long, and every atom will have a future billions of years long. They will outlast you by an enormous margin. They will go on to be part of other things, trees, soil, water, air, and eventually, in the very distant future, they will be part of the quiet dissolving that we have been describing tonight. But not for a very, very, very long time. atoms are gathered together in the shape of you, and that is a remarkable thing, a temporary but magnificent arrangement of matter, capable of thought, of feeling, of rest. In and out, breathe, and let the breath be a reminder that you are alive, that the universe is alive in you, that this moment, this quiet moment in a quiet room, is part of the Stelliferous Era, the brightest chapter of the longest story. Let us cycle back now through the great eras one more time, gently, the way a song might return to its chorus, not because it has forgotten where it was going, but because the melody deserves to be heard again. Right now, in the age of stars, the universe is radiant. 2 trillion galaxies fill the observable cosmos, each one a swirling cloud of light containing billions upon billions of stars. Some of those stars are blue and enormous, burning through their fuel in a few million years and dying in spectacular explosions that seed the cosmos with heavy elements. Some are yellow and steady like our sun, burning for 10 billion years, warming the planets that circle them, giving life the time it needs to take root and grow. And most of them, 70 out of every 100, are red dwarfs, small and cool and patient beyond all reckoning, burning their hydrogen so slowly and so carefully that they will shine for trillions of years, lanterns in the dark that refuse to go out. The second law of thermodynamics is the invisible hand guiding all of this. Energy flows from hot to cold, from concentrated to spread out, from ordered to disordered. Stars shine because they must, because the laws of physics require energy to move from where there is more to where there is less. And starlight is that movement made visible. Every photon that reaches your eye is entropy in action, a tiny parcel of energy moving from a place of abundance to a place of scarcity, smoothing out the universe one ray of light at a time. And when all the smoothing is done, when all the energy has been shared as evenly as it can possibly be shared, the universe will be still. But that is trillions upon trillions of years away, and tonight the sharing continues. The stars are generous, the light is flowing, and the universe is still young enough to be beautiful. The blanket is warm, the room is dark, you are breathing slowly, and the cosmos breathes with you, expanding, contracting, a rhythm as old as time itself. After the stars go out, the universe enters the long twilight of the Degenerate Era, a time of remnants and cooling and extraordinary patience. White dwarfs, those dense porcelain moons left behind by dead stars, drift through the dark, their cores slowly crystallizing into diamond, their surfaces cooling from white to yellow to red to invisible. Each one a tiny jewel in an infinite collection of jewels that no one will ever see. Neutron stars, the collapsed hearts of massive stars, spin slower and slower, their magnetic fields fading, their lighthouse beams dimming until they are just small dark spheres rolling silently through the void. And deep within every remnant, protons may be slowly decaying, the fundamental building blocks of matter dissolving from within, atom by atom, over time scale so long that the word trillion feels like a rounding error. The Degenerate Era is the universe learning to let go, releasing its matter the way you release your grip on wakefulness, slowly, gently, not all at once but bit by bit, until there is almost nothing left to hold. In and out. And then the black hole era, the age vast sentinels. Supermassive black holes, the anchors of once great galaxies, sit alone in the dark, the only structures left, the only objects that could be called objects. They do not shine, they do not burn, they simply exist, massive and silent and patient, while hawking radiation whispers at their edges, stealing their mass one particle at a time, like a river wearing away the face of a cliff, so slowly that 1 billion years of erosion would be invisible to the eye. But the river does not stop, the whisper does not stop, and eventually, after 10 to the power of 100 years, the cliff is gone, the black hole is gone, and the universe is left with nothing but a fading memory of light. The second law has done its work. Energy has been shared as evenly as possible, entropy has been maximized, and the cosmos has reached its deepest possible state of rest. The pillow is soft, the mattress is deep. Your body has found its own state of rest, a warm equilibrium between you and the room, between your thoughts and the silence, between wakefulness and sleep. And beyond the black holes, the dark era, infinite and still, quantum fluctuations murmuring in the void, the universe dreaming in its sleep, tiny, meaningless shivers in a perfect silence that will never be broken. Unless, one day, by some mechanism we do not yet understand, the silence gives way to something new, a new concentration of energy, a new beginning, a new cosmos blooming out of the quantum foam, like a flower growing from bare stone. We do not know if this will happen, we may never know, but the possibility exists, written in the margins of our best theories, a quiet note of hope in the longest story ever told. In and out. You are drifting now, between the story and sleep, between thought and dream, between the universe as it is and the universe as it will be. Let yourself be carried, the way photons are carried through space, the way dust is carried through nebulae, the way planets are carried around their stars, effortlessly, without resistance, part of a motion so vast and so gentle that you cannot feel it, but it is there, always there, holding you, moving you, carrying you forward. The heat death of the universe is not an ending to mourn. It is the natural and beautiful consequence of the laws of physics doing exactly what they do, sharing energy, smoothing differences, finding balance. It is the universe keeping its most ancient promise, the promise that all things in time find rest. And tonight, you are keeping that promise too, in your own small and perfect way, finding rest, finding stillness, finding the quiet at the center of everything. Sleep is your own personal heat death, a temporary cooling, a brief and beautiful equilibrium from which you will emerge tomorrow, refreshed, renewed, the entropy of your mind reset by the mysterious alchemy of dreams. The universe does not get to wake up from its heat death, but you do. You get to wake up and see the stars still shining and feel the sun still warm on your face and know that the Stelliferous Era, this magnificent age of light, is still going strong. That is a gift, the greatest gift the cosmos has to offer, and it is yours every morning for as long as you draw breath. In and out. In and out. Let us linger a while longer, because the night is not over yet and neither is the story, and some things are worth saying twice or 3 times, because sleep does not listen the way waking does. Sleep catches only fragments, phrases, single words carried on the current of breath, and if the right word floats by at the right moment, it can carry you the rest of the way down. Drift. Quiet. Ancient. Vast. Luminous. Eternal. Evaporate. Stillness. Equilibrium. These are the words of the cosmos, the vocabulary of a universe finding its way to peace. And they are the words of sleep, the vocabulary of a body finding its way to rest. Let us think about the universe one more time, from the very beginning to the very end, not in detail this time, but as a single arc, a single breath, a single long, slow exhalation. The Big Bang, a burst of energy so concentrated and so hot that no structure could survive it, pure energy, pure potential, a universe of infinite temperature and infinite density, compressed into a point smaller than an atom. And then expansion, cooling, the energy spreading out, thinning, calming, the first particles forming as the temperature dropped, the first atoms assembling 380,000 years later, hydrogen and helium and a trace of lithium, the simplest elements, the building blocks of everything to come. And then gravity, pulling those atoms together into clouds, into clumps, into the first stars, lighting the dark for the very first time, several 100 million years after the Big Bang, the Stelliferous Era beginning, the universe learning to shine. Generations of stars living and dying, heavy elements being forged and scattered, galaxies forming and merging, the cosmic web taking shape, planets coalescing from dust and gas, and on at least one planet, life emerging, evolving, thinking, wondering. And now, here you are, a thinking being made of star stuff, lying in a bed, in a room, on a planet orbiting a middle-aged star, in a galaxy of several 100 billion stars, in a universe of 2 trillion galaxies, in the Stelliferous Era, the bright warm chapter, the chapter that will one day be looked back upon as the golden age of the cosmos. If it could be looked back upon by anyone, which it cannot, because by then there will be no one left to look. But you are here now, and that is what matters. The room is warm and quiet, the house is still, the street outside is sleeping, the city is sleeping, half the planet is sleeping, turned away from the sun, wrapped in the shadow of the earth, bathed in the faint light of distant stars. In and out. Let us trace the arc forward now, from this moment outward into the deep future. The sun continues to burn for another 5 billion years, warming the inner solar system, sustaining whatever life remains on Earth or wherever life has migrated to by then. Then the sun swells into a red giant, sheds its outer layers, and collapses into a white dwarf, a diamond-hearted ember the size of our planet, slowly cooling in the dark. The Milky Way merges with Andromeda, forming Milkomeda, a giant elliptical galaxy, and then Milkomeda slowly dissolves, its stars scattered, its black hole growing fat on the remnants that spiral inward. The last star is born in about 100 trillion years. The last red dwarf ignites, burns quietly for a few more trillion years, and then goes out. The white dwarfs cool, crystallize into diamond, and then dissolve as their protons decay, over spans of time measured in powers of 10 so large they could fill a page. The black holes sit in the dark, evaporating through Hawking radiation, one particle at a time, for a Google years or more, the last sentinels in a universe that has run out of everything except time and patience. And then the last black hole evaporates in a final flash of light, and the dark era begins, infinite, silent, still, the quantum vacuum murmuring to itself, and nothing, nothing, nothing more. That is the entire story, from beginning to end, from the Big Bang to the heat death, from infinite temperature to near zero, from infinite density to infinite emptiness, from the first light to the last dark. And you have heard it all tonight, or as much of it as your drifting mind chose to catch, and that is enough, more than enough. It is a privilege to hear a story that spans the entire lifetime of the cosmos, and to hear it from a bed in a warm room on a quiet night while the stars are still shining. In and out. Let us speak now about some of the things that make this story less lonely than it might seem. The heat death of the universe is an idea about the very far future, so far that it has no practical bearing on your life or the life of any human who will ever live. Between now and the heat death, there is room for more beauty and more wonder and more discovery than all the minds that have ever existed could contain. There are galaxies we have not seen yet, not because they are hidden, but because we have not looked in the right place at the right time with the right instrument. There are planets we have not discovered yet. Some of them might have oceans, some might have atmospheres, some might have life. There are ideas we have not thought yet, theories we have not formulated, equations we have not written, connections we have not made between things that seem unrelated but turn out to be deeply intertwined. The universe is still surprising us. After 13.8 billion years, it is still full of things we do not understand. Dark matter, dark energy, the nature of consciousness, the origin of life, the reason anything exists at all rather than nothing. These mysteries are not problems to be solved before bedtime. They are invitations to wonder, and wonder is one of the most restful states the human mind can enter, more restful than certainty, more restful than knowledge, because wonder asks nothing of you except to be present and open and still. Be still now. Be present. Be open to the quiet. The universe is vast and ancient and patient, and it has made a place for you inside it, a warm place, a safe place, a place where you can rest. You did not ask to be here, and neither did the universe ask to be here, but here you both are, together, at the same time, in the same cosmos, made of the same materials, governed by the same laws, drifting toward the same quiet equilibrium. There is a strange comfort in that, a companionship that transcends biology, a kinship with the stars themselves. Because you are a star, in a way, a warm body radiating energy into a cool room, burning fuel, creating heat and light and complexity, and eventually, like all stars, you will cool and go quiet. But But not tonight. Tonight you are still burning, still warm, still luminous in your own small way, and the room around you is grateful for your warmth, the way the dark of space is grateful for the light of stars. In and out. In and out. Let us spend a few more moments together in the deep quiet before the story comes to its close. There is a concept in physics called thermal equilibrium. It is when two objects that are in contact with each other have reached the same temperature so that no more heat flows between them. When you first got into bed tonight, the sheets may have felt cool against your skin because there was a temperature difference between your body and the fabric. Heat flowed from you to the sheets, warming them, and the sheets absorbed that heat, and gradually the boundary between you and the bed became invisible. You and the sheets reached the same temperature, and the sensation of coolness disappeared. You are in thermal equilibrium with your bed now, and that is one of the most comfortable states a human body can be in. The boundary between you and your surroundings has softened, blurred, dissolved, and you are held in a cocoon of matched temperature, warm and still and perfectly balanced. This is the heat death of the universe in miniature, a tiny local version of the great cosmic equilibrium, and it feels good. It feels like rest. It feels like peace. In and out. If you could somehow zoom out from your body, out through the roof of your house, up through the atmosphere, past the moon, past Mars and Jupiter and Saturn, past the edge of the solar system, past the nearest stars, past the arms of the Milky Way, out and out and out, until you were looking down at the entire observable universe from some impossible vantage point outside it. You would see a vast web of light filaments of galaxies stretching across billions of light years, connecting clusters and superclusters in an intricate pattern with enormous dark voids between them. The cosmic web, the largest structure in existence. And you would see that it is beautiful. Not beautiful in the way a sunset is beautiful, or a flower, or a face, but beautiful in a deeper way, a structural way, the beauty of something that obeys simple laws and produces extraordinary complexity, the beauty of gravity and thermodynamics and quantum mechanics working together over billions of years to create something that no one designed and no one intended, but that is breathtaking nonetheless. The cosmic web will not last. It will dissolve as the galaxies scatter and the dark energy pushes everything apart. But right now, at this moment in the universe's history, it is here, and it is magnificent. And you are part of it, a small part, an incredibly small part, but a real part, made of the same matter, governed by the same laws, connected to the whole vast structure by gravity and light, and the shared history of 13.8 billion years. The bed holds you, and gravity holds the bed, and gravity holds the earth, and gravity holds the sun, and gravity holds the Milky Way, and gravity holds the cosmic web. You are held all the way up from the mattress to the largest structure in the universe by the same force, the same gentle persistent pull that has been shaping the cosmos since the first second after the Big Bang. In and out. Let us think one final time about entropy, not as a scientific concept, but as a feeling. Entropy feels like letting go. It feels like releasing your grip on something you have been holding too tightly. It feels like the moment when you stop trying to control your thoughts and just let them drift. It feels like the moment when your jaw unclenches and your shoulders drop and your hands open and your breath finds its own rhythm without being told what to do. It feels like the moment when you stop fighting sleep and just surrender to it. That is what the universe is doing, on the grandest possible scale, over the longest possible time. It is letting go. It is releasing its grip on structure and complexity and light, and surrendering to the quiet, to the stillness, to the deep and perfect rest of maximum entropy. You can do the same thing now, in your own small way. Let go of the day, let go of tomorrow, let go of the story, let go of the universe, let go of everything. And rest. The way the cosmos will one day rest, completely, perfectly, without reservation or resistance. In and out. The stars burn on. The red dwarfs glow patiently in the dark. The white dwarfs cool toward diamond silence. The black holes whisper their last warmth into the void. And the universe drifts, slowly, gently, toward the quietest ending ever imagined. And you drift with it, not toward an ending, but toward morning, toward light, toward a new day in the Stelliferous Era, the age of stars, the golden age of the cosmos. Sleep well, traveler. Sleep deeply. Sleep the way the universe sleeps, patiently, completely, without fear. And dream, if you dream at all, of starlight and stillness and the vast, ancient, luminous quiet of the cosmos that made you and holds you and will carry you gently through the night. In and out. In and out. In and out. Good night. And now, as we approach the end of our journey together, let us slow down even further. Let the words come less often and the silences grow longer, the way the intervals between stars grow longer as the Stelliferous Era fades. You are very nearly asleep, or perhaps you are already there, caught in that soft grey region between wakefulness and dreams, where thoughts have shapes but no edges, where sounds arrive from far away, muffled and warm like sunlight through water. Let the last few ideas drift past you like clouds. Take what you want, leave the rest. Nothing needs to be held. The second law of thermodynamics, the gentle engine that drives the universe from light to dark, from hot to cold, from complexity to simplicity, is also the law that drives you from wakefulness to sleep. Your brain has been burning glucose all day, processing information, making decisions, creating thoughts, and now the entropy of your neural activity is increasing. The sharp, focused patterns of consciousness are softening, blurring, spreading out into the warm, diffuse patterns of sleep. This is not something to fight. It is the most natural process in the world, as natural as starlight, as natural as cooling, as natural as the universe itself settling into quiet. In and out. Think of the red dwarfs one last time, those patient lanterns burning for trillions of years, never bright enough to be seen with the naked eye, never dramatic enough to make the news, but always there, always burning, always faithful to their slow, steady purpose. You do not need to be a blue supergiant. You do not need to burn bright and fast and spectacular. You can be a red dwarf, quiet and patient and enduring, burning steadily through the night and still being there, still glowing when the morning comes. The red dwarfs will outlast everything, every supernova, every gamma ray burst, every quasar, every collision of galaxies. The quiet ones endure. And you will endure too, through this night, through the dark hours, through the dreams that come and go. You will endure, and you will wake, and the stars will still be there. In and out. Think of the white dwarfs, those porcelain moons, slowly crystallizing into diamond in the dark, transforming from the inside, becoming something beautiful and permanent and unseen. Sleep is a kind of crystallization too. Your memories solidify, your learning consolidates. The experiences of the day are sorted and stored and woven into the fabric of who you are, all of it happening in the dark, without your conscious awareness, a quiet transformation occurring deep within. You do not need to supervise it. You do not need to understand it. You only need to let it happen, the way the white dwarfs let their cores crystallize, without effort, without resistance, simply allowing the natural process to unfold. In and out. Think of the black holes one last time, those last sentinels, sitting alone in the dark, losing themselves particle by particle to Hawking radiation. They do not fight it, they do not resist it, they simply allow the process to continue, one whisper of energy at a time, until there is nothing left, and where there was something, there is peace. You are losing yourself too, not to Hawking radiation, but to sleep, one thought at a time, one sensation at a time, the edges of your awareness dissolving gently into the dark. Let it happen. It is safe to let go. The universe lets go. The stars let go. The black holes let go. And you can let go too. In and out. The story we have told tonight spans roughly 10 to the power of 100 years, from the present day to the evaporation of the last black hole, a number so large it has no meaning in human terms. And yet, in another sense, the story spans only 2 hours, the time it takes for a voice to carry you from wakefulness to sleep, the time it takes for a body to release its tension and a mind to release its thoughts. 2 hours and 10 to the power of 100 years, both the same story, both ending the same way, in stillness, in quiet, in rest. The universe and you arriving at the same destination, by different roads, at different speeds, but arriving together at peace. In and out. Let us rest now with the cosmos. Let the quantum fluctuations murmur in the void. Let the photons drift through the expanding dark. Let the last faint warmth of the cosmic microwave background wash over everything like a blanket pulled gently over the shoulders of the universe. The universe began as energy, and it will end as energy. The forms will change, the concentrations will shift, the structures will rise and fall, but the energy itself is conserved, always, never created, never destroyed, only transformed. The energy in your body tonight, the warmth in your muscles, the electricity in your neurons, the chemical bonds in your cells, that energy was present at the Big Bang. It has been part of the cosmos for 13.8 billion years. It has been starlight and supernova debris and interstellar dust and ocean water and living tissue. And tonight it is you. And tomorrow it will still be you, and the day after that, and for many, many years to come. And even after you are gone, the energy will continue transformed, redistributed, but never lost. Nothing is ever truly lost. That is the first law of thermodynamics, the conservation of energy, the universe's oldest promise that what exists will always exist in one form or another forever. The second law says that the forms will grow simpler over time. That order will gradually give way to disorder, that heat will spread and cool and balance. But the first law says that everything remains, everything endures, nothing is lost, not one photon, not one particle, not one joule of energy, not one quantum of warmth. You are part of something that has always been and will always be. You are a temporary arrangement of eternal energy, a brief, beautiful pattern in an infinite tapestry. And patterns end, but the tapestry does not. In and out. The night is deep now, the world is quiet. The stars are burning in the sky above the roof that shelters you, burning as they have burned for billions of years, burning as they will continue to burn for trillions more. Somewhere out in the dark, a red dwarf is shining, too dim for any human eye to see, but shining nonetheless, patient and faithful and alone, a tiny warm point of light in a vast cold universe. Somewhere a white dwarf is cooling, its diamond heart growing slowly larger, its surface growing slowly dimmer, a porcelain moon drifting through the dark on a journey that will last longer than the current age of the universe, multiplied by 1,000,000. Somewhere a black hole is sitting at the center of a sleeping galaxy, enormous and silent, while hawking radiation whispers at its edge, stealing mass one particle at a time, the most patient thief in all of nature. And somewhere, in a room, in a house, on a planet orbiting a yellow star, in a galaxy of hundreds of billions of stars, in a universe of 2 trillion galaxies, you are falling asleep. Falling gently, the way light falls through space, the way dust falls through nebulae, the way entropy falls toward equilibrium. Gently, slowly, inevitably, beautifully. The universe tells its stories to sleeping ears just as willingly as to waking ones, and the story will continue even after you have stopped listening, because the universe never stops telling its story. It tells it in starlight and in gravity, in the spin of neutron stars and the glow of nebulae, in the redshift of distant galaxies and the murmur of the cosmic microwave background. It has been telling its story for 13.8 billion years, and it will continue for trillions more, and somewhere inside that story, for a brief and beautiful chapter, you are here. You are here. In and out. In and out. The stars burn on, patiently, endlessly, above you. The room is still. The night is gentle. And now the stars begin to dim behind your thoughts. You are a part of this this cosmos. The carbon in your body was forged in the hearts of ancient stars. I hope you sleep well and dream softly. Good night.